Hello, Irfan sir. Hello.
I'm
Hello.
here.
Yes, sir. I'm audible.
Yes, yes, you are audible.
Yes.
You are audible.
So, on the behalf of Electrical Engineering Department of Tulsiramji Gaikwad Patil College of Engineering, Nagpur, I'm Chetan Jambulkar, Assistant Professor of Electrical Engineering Department. Welcome you all for the AICT sponsored Prerna scheme. And today's expert lecture is delivered by Dr. Irfan Ahmed sir from National Institute of Technology, Durgapur. Sir has done BE, MTech, and PhD, and he has lots of teaching experience, more than 10 years. Sir has many publication to his credit in journal of repute, also in national and international journals or conference. So I am welcome you all for the today's session from the Department of Electrical Engineering. I am welcome you, sir, for today's session. And now I transfer you the session, sir. Irfan, sir.
Okay, thank you, Chetan. Okay.
Ha, sir.
Okay, how many students are here? I need one sort of coordinator
Yes,
because
sir.
when I present my screen, one student, I will call out the name of one student. So,
Okay, sir.
so who can I call?
Hello, sir.
Yes,
Your voice is not. Hello.
not clear.
Yeah.
Now,
Now, yes, clear, sir.
okay.
Yes, sir.
Okay, so I'm going to need one coordinator because when I present my screen, I won't be able to see. So I'll need to call someone.
Yeah, yeah.
So one
Uh,
student, can you
means
nominate someone?
means what to do, sir?
I need the name of one student who I can call. Means when I present my screen, whether I'm audible,
Okay,
whether
okay.
the screen can
Yeah,
be seen. So I need to
yeah,
ask
yeah.
someone.
Okay. Tejaswini Alam is there. Hello,
Tejaswini.
Tejaswini. Ha,
Yes, sir.
ha.
Okay,
So
so
you are.
Tejaswini, I'll be calling her name
Yeah, yes,
whenever
sir.
I need to ask something.
Yeah, yes, sir.
Okay, so let us start. Shall we?
Yes, sir. Yes, sir.
So I've divided this lecture into two parts. The first part I will be teaching. I think you have already studied the subject. Is that correct? Tejaswini, power electronics, you have studied, all of you.
Yeah, yes, sir.
So basically, I will not be teaching, I will be revising the
Yeah,
entire power electronics in 1 hour as far as possible. Then we are
yeah,
going to take a 10 minutes break and then I will be solving some gate questions on power
yeah,
electronics. Okay. Am I audible clearly?
yeah, sir.
Okay, so I'll be presenting my screen now. Okay, Tejaswini, can you see the slides?
Yes, sir.
Hello?
Yes, sir.
Okay.
Visible.
Okay, okay. Okay, so today we are going to have a 2 hours class on power electronics for the gate exam. Okay, okay. Whenever Tejaswini, if you feel I'm going too fast, you tell me to go a little slow. Or if you feel I'm going too slow, you can tell me to go faster. Okay?
Yes, sir.
Okay, so basically this subject power electronics can be divided into three parts. The first part is devices, the second part is circuits, and the third part is applications. You won't get much questions on applications in GATE. The only questions will be on devices and circuits. In fact, devices also not so many questions. The main emphasis will be on circuits. Before we start, I would like to tell you the book from which you need to study. So either you can use P.S. Bhimra, Power Electronics by P.S. Bhimra, or a more suitable or standard book is Power Electronics by M.H. Rashid, R-A-S-H-I-D. So please note down the name of the book, Power Electronics by M.H. Rashid. Okay. And this M.H. Rashid has two books. One is the Power Electronics Handbook. Don't study from the Power Electronics Handbook. Okay. The textbook also, study from the textbook. Or you can use PS Bibra, whatever. Okay, so as far as devices are concerned, the most popular device in power electronics is the silicon controlled rectifier, also known as the SCR, which is a part of the thyristor family. I think all of you have studied SCR in your power electronics course. Is that correct?
Yes, sir.
You had, I think, 1 or 2 units on the SCR.
Yes, yes, sir.
So we'll revise it in short. Now this SCR is a 4-layer device. As you can see on the screen, it has 4 layers, PN. It has 3 junctions, J1, J2, and J3, and it has 3 terminals that are the anode, cathode, and gate. On the right hand side, you can see the circuit symbol of the SCR. The anode is represented by capital A, the cathode is represented by capital K, and the gate is represented by capital G. The difference between a diode and an SCR is that a diode will always conduct whenever it is forward biased, and it will not conduct whenever it is reverse biased. Whereas the SCR, it will not conduct when it is reverse biased. It will also not conduct when it is forward biased until you turn the SCR on. Is that clear, everyone? Tejaswini?
Yes, sir.
Is that clear?
Yes, sir.
So I think you have studied the static VI characteristics of an SCR in your BE syllabus. You have seen this diagram.
Yes, sir. Yeah, yes, sir.
What happens if you forward bias the SCR? Forward bias means?
Three thyristor operation of 3 stages. Forward blocking, reverse, and
Forward blocking, reverse blocking, and forward conduction.
Forward conduction.
So, if you forward bias in SCR, that means you connect anode to positive and cathode to negative. You have 3 junctions here, out of which junctions J1 and J3 are forward biased, but junction J2 is reverse biased. Even when the SCR is forward biased, it does not conduct, it blocks the voltage. If you reverse bias the SCR, anode to negative, cathode to positive, then junctions J1 and J3 are reverse biased, J2 is forward biased. So when the SCR is reverse biased, under that condition also it will not conduct, it will block the voltage. Only when you forward bias the SCR and you turn it on, then the SCR starts conducting. So as you already know, the SCR has 3 regions of operation. One is the reverse blocking region, where it is reverse biased and does not conduct. One is the forward blocking region, where it is forward biased but still does not conduct. And one is the forward conduction region, where it is forward biased and it is turned on so that it starts conducting. I would like to tell you that all the devices that we use in power electronics, they are used as switching devices. Okay, that means they work like a switch. Means they are either on or they are off. When the device is off, the current flowing through the device will be 0. It will behave like a open circuit. And when the device is on, the voltage across the device will be 0. It will behave like a short circuit. Okay, here what is a switching device?
Yes, sir.
Clear,
Yes.
what is a switching device?
Yeah, yes, sir. When is current is of the like a circuit, open circuit.
Yes, so like an open circuit, and when the device is on, it will behave like a short circuit.
Yes.
Or when the device is off, it will behave like an open switch, and when it is on, it will behave like a closed switch. Okay. How do you turn on an SCR? There are 5 methods of turning on an SCR. First of all, you have to forward bias the SCR, and then even without the gate signal, if you go on increasing the anode to cathode voltage, and if this anode to cathode voltage exceeds the breakdown voltage of the CR will turn on. Okay, this is known as forward voltage triggering. However, this may damage the CR. That is why this method of turning on the CR is never used in practice. The second method is you forward bias the CR and you pass a current through the gate of the CR. And you connect the circuit between the gate and the cathode and you pass a current through the gate circuit. So then, even with a small gate current, the CR can turn on. I think you have studied this, right, Tejaswini?
Gate characteristics, sir.
No, gate triggering. Gate characteristics we are not going to study.
Yeah,
And
yes,
if
sir.
you pass the current,
Detail about how to connect means operation of thyroid, so on.
okay, so if you pass a current through the gate circuit, the CR will turn on. There are two more methods of turning on which are not used. One is dV by dt triggering, one is temperature triggering. Those are not used. One more method is light triggering. This is the light activated SCR, where instead of the gate circuit, there is an opening here. And on this opening, whenever you want to turn on the SCR, you put some light. So because of this light, electron hole pairs are created. This junction breaks down and the CR turns on. Okay. You have seen this already, Anna. This also you have studied, switching characteristics of SCRs.
Yes, sir.
Yes. What happens in switching characteristics? Okay, what I want to tell you here is that initially here the SCR is off. So when the SCR is off, the current flowing through the SCR is zero, and the voltage across the SCR will be decided by the supply. When you want to turn on the CR, you are putting a gate voltage, a voltage between the gate and the cathode circuit. So when you apply a gate voltage, the gate current starts increasing. At this point, we can say that the SCR starts turning on. So when the SCR starts turning on, its anode current goes on increasing, whereas its anode to cathode voltage goes on decreasing. At this point, we can say that the CR has turned on. So now the voltage across the CR is very small, ideally zero, whereas the full load current is flowing through the SCR. So this time is called as the turn on time of the SCR. Here the SCR is on. Now when we want to turn off the SCR, what do? We connect an external circuit because of which the CR current starts reducing, and at this point the CR current becomes zero. However, even though the CR current has become zero, the junctions are not yet formed because carriers are still present. Okay. So this is the time required to remove the carriers from the SCR, and this time is called the turn on time of the SCR. So more importantly, what is important in this diagram is that initially when the SCR is off, current through the SCR is zero and it is blocking the supply voltage. To turn on the SCR, we are applying a voltage between the gate and cathode circuit, because of which the gate current starts increasing. At some point, the junction J2 breaks down and the SCR starts to turn on. When the CR is fully on, its anode current is equal to the load current, and the voltage across the CR is ideally zero. It will behave like a short circuit. When we want to turn off the CR, we cannot turn off the CR using the gate circuit. We have to connect an external circuit which will reduce the CR current to zero. After that, the excess charge carriers have to be removed from the CR, and when the excess charge carriers are removed, the CR turns off. Okay, can I move forward?
Yes, sir.
Okay, you have also studied what is latching current and holding current. Is that correct?
Yes, sir.
So these are the definitions of latching current and holding current. Now, when the SCR turns on, its anode current starts increasing. If you remove the gate pulse before the anode current becomes equal to the latching current, the SCR will again turn off. However, if the anode current becomes greater than the latching current, then even if you remove the gate current, the SCR will still remain in the on state. That is why we don't need a continuous gate signal for turning on the SCR. We need simply a pulse. And the duration of the pulse should be such that the SCR anode current should become greater than or equal to the latching current. There is also something called the holding current. If you reduce the SCR current to a value less than the holding current, then the SCR will turn off. For all practical purposes, we assume that the holding current is 0. That means for turning off the SCR current has to be reduced to 0. You have seen this diagram before?
Yes, sir. This is the turn off protection of the SCR.
Yes, this is the thyristor protection circuit. Basically, the thyristor is an electronic device.
This is a 4-meter against the protection of against the di by dt, protection against the dv by dt, and protection against the high voltage, and
Yes.
protection against the high current. This is a 4 method of the protection of SCR.
Correct. For di by dt protection, we use an inductor. For dv by dt protection, we use a snubber circuit, and that is a series combination of RS and CS. For overvoltage protection, we use a non-linear resistor or varistor, we can say. Non-linear resistor means below the breakdown voltage, it will behave like an open circuit, and after the breakdown voltage, it will behave like a short circuit. For overcurrent protection, we are using a circuit breaker and a fuse, which are coordinated. This is the gate circuit protection, overcurrent protection for the gate circuit, overvoltage protection for the gate circuit, and these are if a reverse signal comes, if a noise signal or spurious signal comes to the gate circuit, then to bypass that signal, we are using R1 and C1. In your DE, and all of you are from electrical branch, is that correct?
Yes, sir.
So in your syllabus, you also had series parallel operation of SCRs. We are not going to study that because I have not seen any questions on series parallel operation of SCRs in GATE. Okay? You also studied firing circuits for SCRs, R, RC, UJT. Is that correct?
Yes, sir.
That also we are not going to study because all those firing circuits are no longer used.
Yes.
That is why you do not see those questions also in GATE anymore. Nowadays, SCRs are triggered by using
Commutation.
microcontrollers. Okay? Microcontrollers or digital signal processors or FPGA controllers. Okay? All those firing circuits are RC and UJT. Those things are no longer used. You also studied SCR commutation techniques.
Yes, sir. These are
Class
6
A,
classes.
Class A, Class B, Class C, Class D, Class C, and Class F. We are also not going to study those SCR commutation techniques because again, you do not get any questions in GATE on commutation techniques. The reason is that whenever the supply, we need commutation when the supply is DC, correct?
Yes.
Now, when the supply is DC, we are not using SCRs anymore unless it is a high voltage application. Okay, for low and medium voltage applications, we are using MOSFETs and IGBTs.
Yes.
Okay. Because MOSFETs and IGBTs are fully controllable through their base circuit. You give a signal to the base, the MOSFET or IGBT turns on. You remove the signal from the base, the MOSFET or IGBT turns off. No commutation circuit or technique is required. So whenever the supply is DC, for example, choppers, inverters, we go for MOSFETs and IGBTs. However, when the supply is AC and where you can have natural commutation or line commutation, the SCR is still the preferred device. The commutation techniques are no longer required, and that is why most of the universities have removed commutation techniques from their syllabus. One day Nagpur University also will remove. I don't know when that day will come.
Yes.
Okay, so that was the basics of the SCR. Now we come to circuits. There are three major circuits here, or four major,
Yes.
five major circuits you can say. The first one is the AC to DC converter or rectifier. Basically, AC to DC converters are required whenever the supply is EC and when the supply is AC and you need a variable DC. If you do not need a variable DC, if you need a fixed DC, then you will not use thyristor, you will use a diode. But if you want variable DC, then you use a thyristor. So I'll show some circuits here. I can't cover all of them. I'll just show some of them. So this one you have studied before.
Yes, sir.
So we'll just revise it. So this is a single phase half wave rectifier circuit with a resistive load. You have an AC supply on the input side and the output side we will get DC. This is the supply voltage.
Yes, sir.
Given by Vs is equal to Vm sin omega t. Now when the supply voltage is positive, this SCR is forward biased because anode is connected to positive and cathode is connected to negative. And when the supply voltage is negative, this SCR will be reverse biased.
Reverse bias.
So from 0 to pi, the SCR is forward biased. However, the SCR will not conduct until we give a firing pulse to the gate circuit. And we are giving the firing pulse at the firing angle alpha.
Start a conducting current.
So till alpha, the SCR is forward biased, but it is still off. Because the SCR is off, the output current is 0, the output voltage is also 0. The output voltage is also 0, the output current is 0. At this point, a pulse is given to the gate circuit of the SCR. The SCR turns on, and as soon as it turns on, there is a short circuit here. So the output voltage becomes equal to the supply voltage. As soon as the SCR turns on, the output voltage becomes equal to the supply voltage. Because the load is resistive, the output current is in phase with the output voltage. Output voltage is jumping instantly, so output current is also jumping instantly. Output current increasing, output voltage increasing. Output voltage maximum, output current maximum. Voltage decreasing, current decreasing, voltage 0, current 0. At this point, the SCR current becomes 0. Also, the SCR is reverse biased by the supply voltage, so the SCR turns off. Now the output voltage and output current will both remain 0. Okay, any questions here? Anyone?
No, sir.
Is this output voltage DC? Is the output voltage DC? Yes or no?
Yes.
Yes, the output voltage is DC, but it is not perfect DC. It is a pulsating DC. That means if you perform the Fourier analysis of this output voltage, it will have a DC component as well as a lot of harmonics. Okay, number of harmonics will be present in the output voltage. Supply current and output current are same. Okay, so this is the waveform of the output current as well as the waveform of the supply current. As you can see, the output current as well as the supply current are also DC. Okay, so they also have a DC component as well as a number of harmonics. And the problem here is that the supply is AC, and from this AC supply we are taking a DC current. Okay, so that creates a lot of problems. That is why half wave rectifiers are generally not preferred unless the power requirement is very small. For higher power requirements, we will go for a, before we go there, what happens if you change the load from R to RL? What will be the difference? We are turning on the CR here. Till this point, the output voltage and output current are zero. At this point, we are triggering the CR. Instantly, output voltage becomes equal to the supply voltage. However, because the load is inductive, the output current cannot increase instantly. It will increase gradually. And as you can see, the output current is lagging behind the output voltage. That means the peak of the output voltage comes first, the peak of output current comes later. Output voltage becomes zero first, output current becomes zero later. Till the output current becomes zero, the CR cannot turn off. Till the output current becomes zero, the CR cannot turn off. It will continue to conduct, and as long as the CR is conducting, the output voltage is equal to the supply voltage. As long as the CR is conducting, the output voltage is equal to the supply voltage. As soon as the output current becomes zero, the CR turns off, and both output current and output voltage becomes zero. And again, the cycle is repeated. Okay. Any questions here? Anyone?
No, sir.
Okay. So the effect of the load inductance is that your average output voltage is going to decrease. Again, single phase half wave rectifier. Again, the load is RL, but the difference is now that there is a freewheeling diode connected across the load. So we are triggering the CR here. Till this point, output voltage and source current are zero now. At this point, the CR is triggered. As soon as it is triggered, it behaves like a short circuit. Current flows from supply to a CR load and back to supply. There's a short circuit here, so your output voltage becomes equal to the supply voltage. Your output current both starts to increase. At this point, the supply voltage becomes negative. This terminal becomes positive and this terminal becomes negative. As soon as the supply voltage becomes negative, your freewheeling diode becomes forward biased. And because it is forward biased, your output current now starts flowing through the freewheeling diode. SCR current becomes zero. It is reverse biased by the supply voltage. So your SCR current becomes zero. SCR current becomes zero, source current becomes zero. Your load current is now flowing through the freewheeling diode. Till you once again turn on the SCR and once again it starts conducting. Okay, clear?
Yes.
You can also have an RLE load. Yeah, have you seen an RLE load?
Yes.
Where do you see such type of load?
Yes, sir.
Where do you see this type of load?
No, sir.
This is a very common load. It is the DC motor. This is the armature resistance of the DC motor, armature inductance of the DC motor, and this is the back EMF of the DC motor.
DC motor.
So the only difference between the previous RL load waveform and RLE load waveform is that for RLE load, when the CR is off, the output voltage will be equal to the back EMF. And when the CR is off, the output voltage is equal to the back EMF. Okay. Also, the SCR is forward biased now only from theta 1 to theta 2. Because before theta 1, the supply voltage is less than the back EMF. Supply voltage is less than the back EMF. The anode voltage is less than the cathode voltage. So the SCR is reverse biased from 0 to theta 1. It is also reverse biased after theta 2. Your firing angle alpha has to be greater than theta 1 and less than theta 2. Okay. So those were only for low power. For high power, for high power application, we have to go for a full wave rectifier circuit. And this is a full wave rectifiers. There are two configurations. One is the midpoint configuration and the other is the bridge configuration. Midpoint configuration, the problem is that you need a transformer with a center tapped secondary winding. That is why midpoint configurations are not preferred. The preferred configuration is the bridge configuration. So this is a single phase full wave bridge rectifier, also known as a two pulse rectifier. The previous rectifiers were single pulse. This is a two pulse rectifier. And there are four SCRs here. In the positive half cycle, T1 and T2 are forward biased, and in the negative half cycle, T3 and T4 are forward biased. In the positive half cycle, when you trigger T1 and T2, current flows from supply to T1, load, T2 and back to supply. Supply to T1, load, T2 and back to supply. So your positive of output is connected to positive of supply and negative of output is connected to negative of supply. When T1 and T2 are conducting, output voltage is equal to the supply voltage. And it will remain equal to the supply voltage as long as T1 and T2 are conducting. At this point, we are turning on T3 and T4. Now, the negative half cycle of the supply voltage has started, so T3, T4 are forward biased. We are turning on T3 and T4, and as soon as T3 and T4 are turned on, current flows from supply to T3, load, T4, and back to supply. So now the positive of output is connected to negative of supply, and negative of output is connected to positive of supply. So when T3, T4 are conducting, V0 becomes equal to the negative of the supply voltage. Of course, because this is the negative half cycle, the negative of the supply voltage is positive. Okay. So what we are seeing here is, first of all, the output voltage amplitude has increased. It has actually doubled from the half wave rectifier. Now in one cycle of the supply voltage, there are two pulses of the output voltage. And that is why this is called a two pulse converter or two pulse rectifier. Also, when T1, T2 are conducting, the supply current is positive, and when T3, T4 are conducting, the supply current is negative. Output voltage is still DC, but the supply current is now AC. Okay. So that is why full wave rectifiers are preferable over half wave rectifiers. Any questions here? You also have a half controlled converter, or something that is known as a semi-converter. Basically, there are three types of rectifiers. If all the devices used are diodes, then we say that it is an uncontrolled rectifier. If all the devices used are SCRs, then we call it a fully controlled rectifier. However, if half the devices used are SCRs and half the devices used are diodes, then we call it a half controlled rectifier or semi-converter. Obviously, in half wave circuits, odd number of devices are used. You cannot have half rectifiers and half diodes. You cannot have half controlled half wave rectifiers. But full wave converters, we use even number of devices, so we can have half SCRs and half diodes. Okay, so here we are using two SCRs and two diodes. This freewheeling diode is optional here. Okay. Now what happens in the positive half cycle when you turn on T1, current flows from supply to T1, load, T1 and back to supply. Okay, so when you are turning on T1, output voltage is equal to the supply voltage. At this point, the supply voltage becomes negative, so your freewheeling diode becomes forward biased, and your output current now freewheels through the diode. Because the current is freewheeling through the diode, the output terminals are short circuited. There's a short circuit here, so your output voltage becomes zero. Source current also becomes zero. At this point, we are turning on T2. We are turning on T2. Current flows from supply to T2, load D1 and load D2 and back to supply. Supply to T2, load D2 and back to supply. V0 becomes equal to negative of the supply voltage. It is now positive. Again, here the freewheeling diode conducts and so on. Okay, this is called a single phase half controlled converter or semi-converter. If this freewheeling diode was not there, then positive half cycle T1, D1 conduct. As soon as the negative half cycle starts, T2 becomes forward biased, so then current freewheels through D2 and T1 until we turn on T2. As soon as we turn on T2, current flows from supply to T2, load, T2 and so on. This will continue till again the positive half cycle comes, so that T1 becomes forward biased and then current freewheels through T2 and D1. Okay, so this circuit will work in the same manner even if the freewheeling diode is not present. Okay, so this is called a half controlled converter or semi-converter. The reason for using half controlled converter is that it improves the power factor of the circuit. Okay. This is a three-phase full wave rectifier. Have you studied this in your BE syllabus?
Yes, sir.
We won't go into much detail here. There are 6 devices here, numbered in the sequence in which they become forward biased. That means first T1 will become forward biased, then T2, then T3, then T4, then T5, and then T6. If you do not consider the source inductance, then at any instant of time, only 2 devices will conduct, one from the upper group and one from the lower group, and correspondingly you will get the output voltage. So if T1, T2 are conducting, current will flow from A phase, load, T2 and back to C phase. So your output voltage will be equal to VAC. If T1, T6 are conducting, output voltage will be VAB. If T3, T4 are conducting, output voltage will be VBA. T3, T2 are conducting, output voltage will be VBC, and so on. Okay, so you can have six possible output voltages. In one cycle of the supply voltage, you will have 6 pulses now. Okay, that is why this is called a 6-pulse converter. Also, as you can see, your output voltage is now very much closer to DC as compared to the single phase rectifiers. Okay, this is the reason why 3-phase rectifiers are even better. 3-phase or 6-pulse rectifiers will give you a better DC voltage as compared to single phase rectifiers. In fact, in practice in the industry, you further increase the number of pulses. You go for 12 pulse or 18 pulse rectifiers. Okay. Did you visit HVDC in Chandrapur?
Yes.
HVDC station
Yes,
in Chandrapur. So what was,
yes, sir.
how many pulses rectifier was used there? Did you ask? He must have shown you the diagram. Okay, so in Chandrapur, they are using an 18 pulse rectifier. Okay, so 18 pulse rectifier, the output is almost as good as DC. Okay, almost DC. Enough of rectifiers. Now let us see some DC to DC
DC to DC
converters or
converter.
choppers.
Yes, sir.
Why do we need a
Constant.
DC to DC converter? Yes,
Yes,
Tejaswini?
sir. Constant DC voltage is convert to variable DC voltage.
Yes. So when you want to convert fixed DC to variable DC, you use a DC to DC converter or chopper.
Yes.
We'll see two types of chopper circuits. Lot of chopper circuits are there. We'll see only two here. One is the step down chopper and the other is the step up chopper. Okay, this is the step down chopper circuit. This also you have studied. You have a supply voltage that is a fixed DC. You have a switch. Now this switch can be anything. It can be an SCR, it can be a MOSFET, it can be an IGBT, it can be a transistor. If you are using SCR here, then you can only turn on the SCR using the gate signal. You cannot turn it off. It will not turn off because the supply is DC. So you will need a commutation circuit. Okay, that is why SCRs are not used in choppers unless it is a high voltage application. So you go either for MOSFETs or IGBTs. Now basically in choppers, this switch has to be operated at a very high frequency. Very high frequency means 10 kilohertz, 20 kilohertz. Okay. If you operate this switch at 50 hertz, you will get nothing. Your output waveform will be very, very poor. So this switch has to be operated at a very high frequency, and for high frequency applications, the preferred device is MOSFET. Okay. So you will generally see choppers will employ MOSFETs. Okay, this is your load and then the freewheeling diode here. When the chopper is on, when the chopper is closed, current flows from the supply, load and back to supply. So your output voltage becomes equal to the supply voltage. When the chopper is on, your output voltage is equal to the supply voltage. And when the chopper is off, your output current now freewheels through the freewheeling diode. Okay? So because the freewheeling diode is on, there is a short circuit here. And because there is a short circuit here, your output voltage is 0. Because there is a short circuit here, the output voltage is 0. Again, the chopper turns on, it becomes equal to supply voltage of 0. When the chopper is on, the output current is increasing. When the chopper is off, the output current is decreasing, and so on. So this is your output voltage, which is again not perfect DC. If you perform the Fourier analysis, okay, if you perform the Fourier analysis, it will have a DC component as well as a number of harmonics. ठीक है? क्या रहेगा? DC रहेगा और बहुत सारे harmonics रहेंगे. Now these harmonics are high frequency harmonics. High frequency because the chopper is operating at a high frequency. So these harmonics can be removed by connecting a capacitor here. ठीक है? कभी भी ये जो हम चॉपर सर्किट पढ़ते हैं, ये सर्किट कभी भी यूज नहीं होता है. हमेशा यहाँ पर एक कैपेसिटर लगा रहेगा. There will always be a output filter. So that output filter will remove all the harmonics, and what you will get across the load will be a perfect DC. And what is the value of that DC? That is the average output voltage given by V0 is equal to alpha into the supply voltage. And alpha is your duty cycle given by on time of the chopper divided by the total time. Okay, is this clear?
Yes, sir.
You have studied this circuit also in your BE.
Yes, sir.
This is called a step down chopper. The reason being that your output voltage is always less than the supply voltage. It can never be greater than the supply voltage. The step down chopper is also known as a buck converter. Buck converter, the circuit is slightly different, but the essential working is same. The second type of chopper is the Stepup Chopper, also known as the boost converter. Again, you have a DC supply, you have an inductance, you have a switch, you have a diode, and you have a load. The essential difference is that in the step-down chopper, the inductor was after the diode. And in the step-up chopper, the inductor has to be before the diode. Immediately after the supply, you need the inductor. The step-down chopper, even if you do not have an inductor, no problem. But step-up chopper, the inductor is compulsory. If there is no inductor, you cannot get step-up operation. Now what will happen here? When the switch is closed, current will flow from supply to inductor, switch, and back to supply. Now, because there is a short circuit here, your current goes on increasing. And when you turn off the chopper, instantly the load is connected across the supply, so your current starts decreasing. Because there is an inductor here, earlier inductor current was increasing, the polarity was this terminal was positive and this terminal was negative. As soon as you connect the load, the current tends to decrease, so your inductor voltage reverses its polarity. Now the right terminal becomes positive and left terminal becomes negative. So your output voltage is equal to the supply voltage plus the inductor voltage. Okay, is this clear?
Yes, sir.
If you find out the average output voltage, it is now equal to Vs divided by 1 minus alpha, where alpha is now once again T on by T, that is the duty cycle. T on is the time for which the chopper is on, and T is T on plus T off. T off is the time for which the chopper is off. Okay. This also you have seen, I think.
Yes.
You have also studied. You also studied, I think, types of chopper circuits, class type A, type B, type C, type D, and so on.
Yes, sir.
Anna?
Yes, sir.
I have not seen any gate questions on those types. Okay? These two circuits you should know inside out. Their working, their equations, everything. You should be able to solve gate questions on choppers. Okay? Let us now come to BC2AC converters, also known as inverters. When the supply is DC and we want an
Yes.
AC output, we go for an inverter circuit. We'll start with the simplest inverter, that is the single phase half bridge inverter. Okay. So you have two DC supplies here. You have two SCRs. Once again, because the supply is DC, SCRs are no longer used. You will either use a MOSFET or an IGBT. Low voltage, you go for MOSFET. High voltage, you go for IGBT. The reason being, MOSFETs are much cheaper than IGBTs. But high voltage MOSFETs are not available. High voltage IGBTs are available. So for lower voltage, you use MOSFET. For higher voltages, you use IGBTs. Okay. So what will happen here? Whenever we want the positive half cycle of the output voltage, we'll turn on T1. So current will flow from supply, T1, load, and back to supply. Positive of output connected to positive of supply, negative of output connected to negative of supply. So your output voltage is equal to plus Vs by 2. When you want the negative half cycle, you will turn off T1 and turn on T2. So when T2 is on, current will flow from supply to load, T2, and again back to supply. But now positive of output is connected to negative of supply, and negative is connected to positive. So your output voltage becomes minus Vs by 2. Again T1 plus Vs by 2, again T2 minus Vs by 2, and so on. Is this clear?
Yes, sir.
Yes. Okay. There are some basic questions here. First one is, why do we need the diodes D1 and D2? Basically, what happens here is, when T1 is on, current is flowing like this. Now, when we turn off T1 and turn on T2, this current, if the load is inductive, this current cannot reverse instantly, so it will continue to flow in this direction. But now this T1 is off, so it cannot go like this. It also cannot flow like this because it cannot flow opposite to D1. So this current will now flow through D2 and it will reduce to 0. And once it is 0, if your T2 is turned on, it will now start flowing through T2. Okay? So basically, these D1 and D2, they are feeding power back to the supply. Okay? They are called as feedback diodes. Achha. Second question is, this output voltage that you are seeing, is this AC or DC? Yes, AC or DC? It is AC. Is it sinusoidal AC? No.
No, sir.
So it has a fundamental component, plus it also has a lot of harmonics. Okay?
Yes, sir.
What I am going to say is very important, so listen carefully. It has a lot of harmonics. If your positive area is equal to the negative area, there will be no even harmonics. Okay? If your positive area is equal to the negative area, there will be no even harmonics. Only odd harmonics will be present. Now the odd harmonics also depend on which inverter you are using. Single phase inverters will have all odd harmonics. Third, fifth, seventh, ninth, 11th, 13th, every odd harmonic will be present. If you go for a three-phase inverter, it will not have any triplen harmonics. Harmonics will be of the order 6n plus minus 1, where n is an integer. Okay, so when you put n is equal to 1, you get 5th and 7th harmonic. When you put n is equal to 2, you get 11th and 13th harmonic, and so on. If you are using a three-phase inverter, it will have a fundamental component plus 5th, 7th, 11th, 13th, 17th, 19th, all these harmonics will be present. Okay, is that clear?
Yes, sir.
Third question. Can we control the frequency of the output voltage? Can we control the frequency of the output voltage? The answer is yes, because these durations are in our control. If we decrease these durations, if we change the waveform like this, the output frequency increases. If we increase these durations, if we make the waveform like this, the output frequency decreases. Okay? So we can control the output frequency. Can we control the output voltage? Can we control the output voltage?
Yes, sir.
Okay, so I'm controlling the inverter so that I get this type of output voltage in the first case. And in the second case, I'm again controlling the inverter. to get this type of output voltage. Okay, this is the first one, first waveform. This is the second waveform. Okay, so my question is, which waveform has the highest? Which waveform has more frequency, first or second? Tejaswini, which waveform has more frequency, greater frequency?
First.
The first one, the frequency is greater. Which waveform has greater amplitude, magnitude? कौन से waveform का magnitude ज़्यादा है, first or second?
Sir, first.
कौन से waveform का magnitude ज़्यादा है, first या second? Anyone? The answer is दोनों का magnitude same है. The magnitudes of both the waveforms are same. Is this clear?
Yes.
If you see till here, the positive parts, if you add, they are the same. The negative parts, if you add, they are also the same. So both the waveforms have the same amplitude. Okay? So here we can only control the frequency. We cannot control the amplitude. If you want to control the voltage, you have to go for pulse width modulation. Okay? PWM.
Yes, sir.
This is a single phase full bridge inverter. And the problem with the single phase half bridge inverter was you required 2 DC supplies, okay, which is not good. So you go for single phase full bridge inverter where you need only a single DC supply now, and instead of 2 devices, you need 4 devices, 4 SCRs and 4 diodes. The rest of the working is same. You turn on T1 and T2, output voltage becomes equal to supply voltage. You turn on T3 and T4, output voltage becomes equal to negative of the supply voltage. This also you have studied, 3-phase bridge inverter.
Yes, sir.
Yes. You have seen there are 2 modes of operation, 120 degrees mode and 180 degrees mode. You have drawn the waveforms also. And you always get a 7-mark question on either the 120 degree mode or 180 degree mode. So all of you know the waveforms. Okay, I will not repeat the waveforms. Okay. The fourth device, the fourth circuit, not device, the fourth circuit is that of an AC voltage controller. Did you study AC voltage controller in BE?
Yes.
This is a single phase AC voltage controller wherein either you can use a triac or you can use 2 SCRs in anti-parallel. In the positive half cycle, T1 will be forward biased, negative half cycle, T2 will be forward biased. Firing angles of both the SCRs will be same. In the positive half cycle, you are turning on T1, this is the output voltage you are getting. Here T1, T2 both are off. Now here you turn on T2, so this is the output voltage that you are getting. So basically by controlling the value of alpha, you can control the amplitude of the output voltage. Okay. So this is an AC voltage controller. It will control or it will convert your fixed AC to variable voltage AC, but it cannot change the frequency. Your output frequency and input frequency are same. Okay?
Yes, sir.
If your alpha is 0, you will get your maximum output voltage that will be equal to the supply voltage. As you go on increasing the value of alpha, your output voltage goes on decreasing. If your firing angle becomes equal to pi, your output voltage will be 0. Correct?
Yes.
If your firing angle becomes equal to pi, you turn on T1 here, and here T1 also will turn off. Then T2 will turn on here, turn off also here. So if your firing angle becomes equal to pi, your output voltage will be 0. The last circuit is a cycloconverter, which you have studied in your BE. I have not
Yes.
seen any questions on cycloconverter. The reason being cycloconverters are very, what do you say, complex, complex circuits. Okay? So generally, cycloconverters are not seen. Nowadays, nobody uses cycloconverters unless you have high power application. Okay? Cycloconverters are used only for high power applications. Otherwise, what do we use is an AC to DC converter followed by a DC to AC converter. Okay? AC to DC converter to convert AC to DC, and then a DC to AC converter to convert that fixed DC to variable voltage, variable frequency AC. That is what is used. If there is high power application, high power means megawatt range, then cycloconverters are still being used. Okay, so that was a review of the power electronics. We'll take a 10 minutes break now and we'll restart at 3:40 p.m. and we'll see some gate questions. Okay?
Yes, sir.
Okay. So I'll rejoin at 3:40 p.m. Okay? Okay, so can we restart? Yes, can we start again?
Yes, sir.
Okay, so the next part of the session will concentrate on some gate questions. So I would like to tell you that you go through some gate questions, gate question papers, and see the topics that come in gate. You prepare very, very thoroughly.
Yes.
Okay, so I'm going to present my screen again. Okay. Can you see the screen, Tejaswini?
Yes, sir. Visible.
So basically you have two types of questions, 1 mark questions and 2 mark questions. 1 mark questions are simpler and 2 mark questions will be slightly more complex. Okay, so we'll start with 1 mark questions. I've started from the previous year's paper, that is 2020. So this was the first question in 2020. At thyristor T1 is triggered at an angle alpha and degree. First of all, which circuit is this? This is the AC voltage controller circuit that we had just seen. So the question is that this thyristor T1 is triggered at an angle alpha and T2 is triggered at an angle of 180 degrees plus alpha in each half cycle of the sinusoidal input voltage. Assume both thyristors to be ideal. Now to control the load power over the range of 0 to 2 kilowatt, the minimum range of variation in alpha is. How do you solve this question? Yes, anyone? The thing is, this is a very simple question. Now, the load power in the range of 0 to 2 kilowatt. Now, we've just seen that for the output current and hence the output power to be 0, the firing angle should be 180 degrees. So because here one side of the range is 0 and because here there is only one answer which has 180 degrees. So directly without doing any calculation, you can say that the right option is D. Am I clear?
Yes, sir.
So you see how simple the question is. They are saying that the load power has to be controlled from 0 to 2 kilowatt because one side is 0. And you know that for the output power to be 0, the firing angle has to be 180 degrees. And there is only one option which has 180 degrees. So directly you can write that the correct option is D. Okay. Can I move forward?
Yes, sir.
Can I move to the next question? This is the next question. Single phase inverter. We saw single phase inverters, correct? This was the single phase inverter. So a single phase inverter is fed from a 100-volt DC source. Okay. The DC source is 100 volt and is controlled using a quasi-square wave modulation scheme to produce an output waveform V of t as shown. This is the output waveform V of t. As I told you, the circuit that we saw, You can control the output frequency, but you cannot control the output voltage. If you want to control the output voltage, you have to go for pulse width modulation. So pulse width modulation, there are three types. There were three types in your syllabus. One was single pulse modulation, second was multiple pulse modulation, and the third was sinusoidal pulse width modulation. Am I correct, Tejaswini?
Yes, sir.
So I have seen a lot of questions on single pulse modulation, and this is also a question on single pulse modulation. Okay. So the single phase inverter is controlled to produce an output waveform V of t as shown. The angle sigma is adjusted. The angle sigma is adjusted. This is the angle sigma. Is adjusted to entirely eliminate the third harmonic component from the output voltage. Under this condition for V of t, the magnitude of the fifth harmonic component as a percentage of the magnitude of the fundamental component is. The question clear?
Yes, sir.
We are controlling the output voltage such that the third harmonic component is 0. And I told you that here for single phase inverters, the output voltage will have fundamental as well as third, fifth, seventh, ninth, all odd harmonics will be present. Now we are controlling the output voltage so that the third harmonic is 0, and we have to find the fifth harmonic component as a percentage of the fundamental. That is the question. So before we solve this question, I am going to show you single pulse modulation. Very clearly. Okay. This was the output voltage without any pulse width modulation. Correct. This was the output voltage without any pulse width modulation. This is what we call a square wave. This is what we call a square wave, and it has all harmonics, all odd harmonics. Now in single pulse modulation, what we do, instead of getting the whole pulse at the output, we control the pulse width. And single pulse means in one half cycle there will be only one pulse. So here you see in the positive half cycle there is one pulse, in the negative half cycle there is one pulse. This is called as single pulse modulation. Multiple pulses in each half cycle there will be more than one pulse. As you can see, the pulse is centered around pi by 2. We do not want even harmonics, the pulse has to be centered around pi by 2. And the width of the pulse is 2d. The width of the pulse is 2d. D on this side and D on this side. Okay. I will forget about what is written in the question and will concentrate here. Now this output voltage, if you perform the Fourier analysis, this is the equation for the output voltage. Summation n is equal to 1, 3, 5 and so on up to infinity. 4 Vs by n pi, where Vs is the supply voltage, sine n by 2, sine nd, sine n omega t. Is this clear?
Yes, sir.
Yes. Now in the question, it says that the third harmonic component is 0. Now for the third harmonic component to 0, we cannot make this 0. This term cannot be made 0. This will be 0 only when n is infinite. And this n is the number of the harmonic.
Yes, sir.
This will be 0 only when n is infinite, so this cannot be made 0. This will be either +1 or -1. If n is odd, it will be odd multiple of sine of odd multiple of pi by 2, that is +1. If n is, sorry, n will only be odd, but for values 1, 3, 5, for all values this is +1 only. So this term is either +1 or -1. This also cannot be made 0. The only term that can be made 0 is sine nd. Correct? The only term that can be made 0 is sine nd. So if you make sine nd and a third harmonic, So for third harmonic n is 3. So you are saying that sine 3d should be equal to 0. Sine 3d will be equal to 0 when 3d is equal to 180 degrees. Correct? Because sine 180 is 0.
0.
So sine 3d will be 0 when 3d is equal to 180 degrees or d is equal to 60 degrees. So if you make d equal to 60, then your third harmonic component becomes 0. Is that clear?
Yes.
Yes? Yes. So from this waveform, if you want to remove the third harmonic, what do? You make the pulse width 60 plus 60, that is 120. Okay? Then your third harmonic will be 0. So for the third harmonic to be 0, this pulse width has to be 120 degrees or d has to be 60 degrees. Then what is the magnitude of the fifth harmonic? Magnitude of the fifth harmonic will be 4 Bs by 5 pi sine 5 pi by 2 sine 5d. Okay, we are putting the value of n is equal to 5 and the value of d we have already calculated. The value of d is 60 degrees. So from this you will find the fifth magnitude of the fifth harmonic. We'll divide that by magnitude of the fundamental. What is magnitude of the fundamental? We'll put n is equal to 1. That is 4 Bs by pi sine pi by 2 sine d. Okay, is this clear?
Yes.
Everyone? There is one unknown here, and that unknown is d. So to find the value of that unknown, they have given one condition, and the condition is that the third harmonic should be 0. You put the condition sine 3d equal to 0 and you find the value of d. That gives you the value of d. Then you find the magnitude of the fifth harmonic by putting n is equal to 5. Then you find the magnitude of the fundamental component by putting n is equal to 1. You divide the third harmonic by divide the fifth harmonic by the fundamental, and the answer that you will get is 0.2 or 20%. Is that clear?
Yes.
Shall I move to the next question? Okay. Remember this diagram. This is given in PS Bimra. Remember this diagram and this equation that solves a lot of questions in GATE. Go to the next question now, 2019. And this question says that a 6-pulse thyristor bridge rectifier. 6 pulse means 3 phase. 3 phase full wave thyristor bridge rectifier is connected to a balanced 3 phase 50 Hz AC supply. Assuming that the DC output current of the rectifier is constant. When will the output current of the rectifier be constant? When your load inductance is very high, then the output current will be constant. What is the lowest harmonic component in the AC input current? This is your 3-phase full wave rectifier. This is your AC side, this is your DC side. If your load inductance is very high, your output current will be constant, provided of course that the firing angle is less than 90 degrees. So, in this question, the load inductance is very high, your output current is constant, and they are asking on the AC side, what is the, what are they asking? On the AC side, what is the lowest harmonic component? Okay. What is the answer? You study these rectifiers. Yes. Rectifier that you studied. Okay, so I'll say this line is pi. This line is pi and this line is 2 pi. Okay. will happen here? Okay, can you see this waveform? Can you see this waveform clearly? Yes, Tejaswini? Can you see the red color waveform?
Yes, sir.
So this is the waveform of the phase current for a three-phase full wave rectifier when the output current is constant.
Yes, sir.
This angle,
Firing
this
angle.
angle is 120 degrees. This angle is 120 degrees. This is the firing angle. This will be 60. This will be 60. Again 60, 120, 60. And we have just seen in the previous question that for an AC waveform where this is 120 degrees, the third harmonic is 0. Correct?
Yes, sir.
Yes, so the lowest harmonic will be the fifth harmonic. And because the supply frequency is 50 hertz,
50 hertz.
the fifth harmonic is 250 hertz. So the answer to this question is 250 hertz. Okay. So you could solve this question very quickly if you know that for a 6-pulse thyristor bridge rectifier, the input AC current is quasi square wave. But the conduction angle is 120 degrees. And because it is quasi square wave, this is the quasi square wave. This one is a quasi square wave. This is a square wave. This is a quasi square wave. And for a quasi square wave, the third harmonic becomes 0. Quasi square wave means 120 degrees, 120 degrees, 60, 60, 60, 60. So for a quasi square wave, the third harmonic is 0. The lowest harmonic is the fifth harmonic. So you know that because the supply frequency is 50 hertz, the lowest harmonic will be 250 hertz. Okay, clear?
Yes, sir.
Okay, so very simple question. The only thing is you should know that for a 6-pulse bridge rectifier, the lowest and the AC current is quasi square wave, so third harmonic is 0, lowest harmonic is fifth. After the fifth harmonic, you will have the 7th harmonic, then 11th harmonic, 13th harmonic, and so on. Okay. I'll go to the next question now. Output voltage of a single phase full bridge voltage source inverter. Once again, we have single phase full bridge voltage source inverter. This is the single phase full bridge voltage source inverter. It's controlled by unipolar PWM with 1 pulse per half cycle. 1 pulse per half cycle means once again we are dealing with single pulse modulation, 1 pulse per half cycle. For the fundamental RMS component of output voltage to be 75% of DC voltage. Okay? For the fundamental RMS component of output voltage to be 75% of DC voltage, the required pulse width in degrees is. Okay? So, what is the fundamental RMS component of output voltage? What is the fundamental component? We will put n is equal to 1. So, fundamental component is 4 Vs by pi sine pi by 2. Okay, sine pi by 2 is 1. So, you can forget about this. It is 4 Vs by pi sine d. 4 Vs by pi sine d. This is the fundamental component that you get by putting n is equal to 1.
1.
This value that I just said, 4 Vs by pi sine d, this value, is it the RMS value?
Yes, sir.
No, it is the maximum value. It is not the RMS value, it is the maximum value. What will be the RMS value? It will be 4 Vs upon pi sine d divided by root 2.
Root 2.
4 Vs by pi sine d divided by root 2. That is the RMS value. And he's saying that this should be equal to 75% of DC voltage. How much is the DC voltage? DC voltage is Vs. So 4 Vs by pi sine d divided by root 2, that must be equal to 0.75 multiplied by Vs. And 75% is 0.75. So Vs will get cancelled, and if you calculate, you will get D is equal to 56.41 degree. Okay? Vs will get cancelled, and if you calculate, you will get D is equal to 56.41 degree. But what has he asked? He has asked for the pulse width. So the pulse width is 2D. The pulse width is 2D. So 2 multiplied by 56.41 becomes equal to 112.8 degrees. That is the answer to this question. Am I clear?
Sir, can you repeat?
Yes. Fundamental component is 4 Vs by pi sine d. Okay, that is the maximum value. RMS value is 4 Vs by pi sine d, everything divided by root 2.
Yes.
Okay. And he's saying this should be equal to 75% of the DC voltage. That means this must be equal to 0.75 into Vs. So 4 Vs. Vs divided by
Root 2.
Vs by pi multiplied by sine d. Okay. This is your 4 Vs by pi multiplied by sine d. This is your maximum value. What will be the RMS value? It will be a factor of root 2 here divided by root 2. Okay, so I'll simply write root 2 here instead of searching for the symbol. Okay. So 4 Vs by root 2 pi into sine d, that must be equal to 75% of Vs. So that must be equal to 0.75 multiplied by Vs. Okay, this is your equation. Vs get cancelled. Okay. So 4 by root 2 pi sine d is equal to 0.75. If you calculate this, D comes out to be equal to 56.41 degrees. Okay, is this clear?
Yes, sir.
But it asks for the pulse width. Pulse width is how much? Pulse width is 2D. If you find out pulse width, 2D, that will be 56.41 multiplied by 2. Okay, so that is equal to 112.8 degrees. Okay, that is the answer to this question. Now it is clear?
Yes, sir.
Let us go to the next question. A single phase, fully controlled rectifier is supplying a load with an anti-parallel diode. Just 1 minute, I'm coming. 1 minute.
Yes.
Can you hear me? Tejaswini?
Yes, sir.
Okay, so the next question is from 2018. A single phase fully controlled rectifier is supplying a load with an anti-parallel diode as shown in the figure. All switches and diodes are ideal. Which one of the following is true for instantaneous load voltage and current? Okay, so there are 4 conditions given here. Now, what is the right answer? Single phase full wave fully controlled rectifier with the freewheeling diode. What will happen? Positive half cycle, let us say this terminal is positive, this terminal is negative. The positive half cycle current will flow like this. As soon as the negative half cycle starts, the current will freewheel through the freewheeling diode until you trigger T3 and T4, and then the current will flow in this manner. So, which of these is true? First of all, the output current is always flowing in the same direction. Correct? The output current is always positive. The output current cannot be negative. And because the output current cannot be negative, A and B cannot be an option. Because A says that the output current is negative, B also says that the output current is negative. And because the output current cannot flow in the opposite direction, A and B are not possible options. Okay, is that clear?
Yes, sir.
C and D both are saying that the output current is greater than or equal to 0. That means the output current is positive. So either the answer is C or D. That depends on the voltage. C says that the output voltage is positive. D says that the output voltage is negative. Can the output voltage be negative? Instantaneous. At any instant, the output voltage cannot be negative. It will either be positive or it will be 0. When the freewheeling diode is conducting, the output voltage is 0. So the correct option is C. The output voltage is either positive or 0. Output current is also positive. D is not possible because of the freewheeling diode. If the freewheeling diode was not there, then as we have seen for an inductive load, the instantaneous output voltage can be negative also. But because the freewheeling diode is there, the output voltage cannot be negative. So D is the wrong option. The correct option is C. Okay, clear?
Yes, sir.
So I hope you are feeling that the questions are easy. Are you feeling that?
Yes, sir.
Remaining people, if I can make you feel that the questions are easy, then my job today is done. Okay? I can't teach you power electronics today. I can only make you feel that you can solve gate power electronics questions. Okay. Let us go to the next question. The waveform of the current drawn by a semiconductor from a sinusoidal AC voltage source is shown in the figure. If I0, this is I0, if I0 is equal to 20 ampere, the RMS value of fundamental component of the current is. This is your semiconductor. A single phase half controlled converter or semiconductor. So this question that we are just seeing deals with this topic. Now, as you can see, when T1 is triggered, until T1 is triggered, there is freewheeling here. When T1 is triggered, current starts flowing. At this point, again, current freewheels, the source current becomes 0. Then T2 is triggered, so source current becomes negative, and so on. Okay. So what you need to know to solve this question is that for a single phase semi-converter, the source current RMS value of fundamental component of the source current is 2 root 2 upon pi multiplied by I0 multiplied by cos alpha by 2. Okay. Straight formula. So this simple straight formula question. RMS value of fundamental component of the current is 2 root 2 upon pi multiplied by I0 multiplied by cos alpha by 2. I0 is given as 20 ampere and the value of alpha is given as 30 degrees. If we substitute the values, the answer that you get is 17.39 ampere. Okay. Clear?
Yes, sir.
So you have to see the formula for what we say fundamental component of source current. RMS value of fundamental component of source current for both semi-converter as well as full converter, full wave fully controlled converter. And memorize both the formulae. Okay? You'll get that in Kimra's book. Let us come to the next question. Phase controlled single phase full bridge converter. This is a phase controlled single phase full bridge converter supplying a highly inductive DC load. Okay. Whenever it says that it is supplying a highly inductive DC load, it means that the output current is constant. Here you see that the output current is increasing slightly, decreasing slightly. But if the load inductance is very high, the output current becomes constant. And if the output current is constant, the supply current becomes the square wave. Supply current will be a square wave. Is this clear?
Yes.
Yes, the supply current will be a square wave. The fundamental frequency in hertz of the voltage ripple on the DC side is the fundamental frequency in hertz of the voltage ripple. This is the DC side. DC side means output. What is the fundamental frequency in hertz of the voltage ripple? What is the answer? Anyone? If this is 50 hertz, what is this frequency? Yes. Anyone? Tejaswini?
Yes, sir.
What is the frequency of this?
50 hertz, sir.
Of this ripple? No, this is 50 hertz. What is this frequency? It is 100 hertz. Anna? In one cycle of 50 hertz, you are getting 2.
Yeah, yes, sir.
Yes. So if this is 50 hertz, the ripple frequency is 100 hertz. That is why the answer to this question is 100. Okay?
Yes.
Yes. Okay. Very simply, single phase half wave rectifier or one pulse converter, ripple frequency will be same as the supply frequency, 50 hertz. Single phase full wave rectifier or two pulse converter, ripple frequency will be double the supply frequency. Three phase half wave rectifier or 3 pulse converter, ripple frequency will be 3 times the supply frequency. 3-phase full wave rectifier. 3-phase full wave rectifier. Ripple frequency is 6 times the supply frequency, 6 pulse converter. And now one cycle is from 0 to 2 pi. So in one cycle of the supply, you are getting 6 ripples. So the ripple frequency is 6 multiplied by 50, that is 300 hertz. Okay? So this question, all you have to see is which converter. Single phase half bridge, the answer is 50. Single phase full bridge, the answer is 100. 3-phase half bridge or 3-phase half wave, the answer is 150. 3-phase full bridge, the answer is 300. Okay, clear? Yes? Tejaswini, yes or
Yes.
no?
Yes, sir.
Okay. In the circuit shown, the diodes are ideal. Okay. Ideal diode means instant on, instant off. Okay. Forward biased on, reverse biased off. When the diode is on, behaves like a perfect short circuit. When the diode is off, behaves like a perfect open circuit. That is an ideal diode. Because in this circuit, the diodes are ideal. The inductance is small. This inductance is small, but it is not zero. It is small, but it is not zero. And this current is not equal to zero. This current is not equal to zero. Which one of the following statements is true? 4 statements are given here. D1 conducts for D1 conducts for greater than 180 degrees and D2 conducts for greater than 180 degrees. D2 conducts for more than 180 degrees and D1 conducts for 180 degrees and so on. Okay. 4 statements are given. And we have to tell which one of the statements is correct. Okay. So what will happen here basically is during positive half cycle, current will start flowing like this.
Yes, sir.
Correct?
This is a forward bias plus.
D1 is forward biased, so positive half cycle for 180 degrees, D1 is conducting. Okay. Now when the negative half cycle starts, the current is gradually, negative half cycle, can current flow like this?
Yes.
Can it flow? No, because of this diode.
Yes.
Can current flow like this? No, because of this diode. When the negative half cycle, what will happen? This current, this is the current source. This current cannot become zero. This current is not zero. It has been clearly mentioned, and this current is constant because it is a current source. So negative half cycle, this current will flow through the diode D2. The positive half cycle, the current is flowing like this. When the negative half cycle starts, this current has to reduce from I0 to 0. But because there is an inductance, this transition cannot happen in 0 time. It will take some time for this current to reduce to 0. That is why D1 will conduct for some time greater than 180 degrees. Okay? And D2 will also conduct. When at the end of the negative half cycle, this current cannot instantly become I0. So for the negative, at the end of the negative half cycle, for some time, D1 as well as D2 will conduct. Okay, so the answer to this question is A. D1 conducts for greater than 180 degrees and D2 also conducts for greater than 180 degrees. Okay. Was that clear?
Yes, sir.
Because of inductance. If there is no inductance, then both of them conduct for 180 degrees. But because of the inductance, V1 will require some time for the current to reduce to zero, as well as for the current to rise to zero. Okay, this question, the next question is purely formula based. Okay, you see the formula, it is available in Bhimra. Yes, Bhimra book. P-phase voltage source inverter operating in 180 degrees conduction mode. Star connected resistive load. DC voltage input is VDC. What is the peak of the fundamental component of the phase voltage? Okay, the answer is 2 VDC upon pi. You can see the formula is available in any power electronics book. You will get the formula. Okay, formula you have to remember. Go to the next question. The figure below shows the circuit diagram of a controlled rectifier supplied from a 230 volt 50 hertz single phase voltage source and a 10:1 ideal transformer. Assume that all devices are ideal. The firing angles of thyristors T1 and T2 are 90 degrees and 270 degrees respectively. Okay, this is a single phase half controlled single phase semi-converter that we had seen. The RMS value of the current through the diode D3 in amperes is. How to find this? How to find this? Can anyone tell me the answer instantly? Does anyone know the answer? There is a very basic principle in power electronics. And the basic principle is that if your load is resistive, then your freewheeling diode is useless. Okay? What is the basic principle? If your load is resistive, your freewheeling diode is useless. Why? Because in the positive half cycle, you are turning on T1, current is flowing from supply, T1, load, D2 back to supply. Because the load is resistive, when the voltage becomes zero, this current also becomes zero. Okay. So no voltage, no current. Negative half cycle, you turn on T2, current flows through supply, T2, load, D1 back to supply. Once again, when the voltage becomes zero, the current becomes zero. So, no current will flow through the freewheeling diode when the load is resistive. And that is why the RMS value of the current through diode D3 in amperes is 0. Okay, clear?
Yes, sir.
If there had been an inductance, then positive half cycle T1 D2 conduct, negative half cycle starts, current freewheels through the diode. Then you have to find the value of the current. But for resistive load, there is no freewheeling. Your freewheeling diode is useless. No current will flow through the freewheeling diode. Okay. Next question. A buck converter. Buck means step down. A buck converter, as shown in figure below, is working in steady state. It is working in steady state. The output voltage and the inductor current can be assumed to be ripple free. The output voltage is ripple free means it is constant. Inductor current is also constant. Inductor current is constant. Figure B shows the inductor voltage VL during a complete switching interval. This is inductor voltage VL during a complete switching interval. This is the on time, this is the off time. Assuming all devices are ideal, the duty cycle of the buck converter is. To find the duty cycle alpha of this buck converter or step-up chopper. How will we do that? Yes, which principle you will use? You will use the principle that because the inductor is ideal, there are no losses in the inductor. That means energy stored by the inductor must be equal to energy released by the inductor. Or because the inductor current is constant, we can use the volt-second balancing principle. What can we use? Volt-second balancing principle. Okay, you write this down, volt-second balancing principle, search it on Google. Okay. As soon as you use the volt-second balancing principle, this becomes a very, very simple question. Volt-second balancing principle says that 30 volt multiplied by T on must be equal to 20 volt multiplied by T off. Okay? 30 volt multiplied by T on must be equal to 20 volt multiplied by T off. And if you do that, your duty cycle comes out to be 0.4. And duty cycle will be T on divided by T on plus T off, or T on by T. So that comes out to be 0.4. Okay. So that's here. What do you say? Is enough?
Thank you.
Want to see some more questions?
Sir, if you are free, then take at least your more question there. They give me the more concept.
Means right now or next, or you want one more lecture? What are you saying?
Sir, if you are not free, then to give the two question more.
Okay.
Give the basic concept.
Okay. We'll see some more questions. Let
Yes,
us
sir.
see one 2-mark question. Okay. So in the DC to DC converter circuit shown, okay, this is a DC to DC converter circuit. These are 2-mark questions. Okay, so slightly more harder. Switch Q, switch capital Q, switch capital Q is switched at a frequency of 10 kilohertz. Okay, 10 kilohertz means one cycle will be how much? 10 kilohertz. 1 divided by 10 to the power 3. 0.1 millisecond, or 100 microsecond. Okay, one cycle is 100 microsecond or 0.1 millisecond. So this switch Q is switched at a frequency of 10 kilohertz with a duty ratio of 0.6. Duty ratio of 0.6 means 100 microsecond may say 60 microsecond it will be on and 40 microsecond it will be off. Okay, is this clear?
Yes.
10 kilohertz means one cycle is 100 microsecond, duty ratio is 0.6. So for 60 microsecond it will be on and 40 microsecond it will be off. All components of the circuit are ideal and the initial current in the inductor is 0. The initial current in the inductor is 0. We have to find the energy stored in the inductor in millijoules at the end of 10 complete switching cycles. Energy stored in the inductor in millijoules at the end of 10 complete switching cycles. So to find the energy stored in the inductor, basically we have to find the current flowing in the inductor at the end of 10 cycles. Okay, that is what we have to find. Now let us see this circuit, how it will work. When this switch is closed, current will flow from this supply to the inductor, through the switch, and back to this supply. Correct? This is what will happen when the switch is closed. And when you open the switch, okay, when you open the switch, this inductor current cannot reduce to zero instantly. So it will now flow like this. Is this clear, everyone?
Yes.
For 60 microsecond, this is the flow of the inductor current. And then for 40 microsecond, this is the flow of the inductor current. For 60 microsecond, your inductor current is increasing. And will it increase or decrease?
Increase
It will increase, because there is a
on.
short circuit. There's a short circuit here, so your inductor current will increase. And for 40 microsecond, your inductor current will decrease.
Decrease.
Increase because the supply is increasing the current, and decrease because now it is flowing against the supply, so your current will decrease. Okay, this much is clear. Now the question is, when it is increasing, what will be the nature of the current? Will it be sinusoidal? Will it be exponential? Will it be a straight line? Basically, we already know that inductor current is given by V is equal to L EI by dt. Correct?
Yes.
You have studied in first year. Inductor voltage is given by L di by dt. Or we can say that for an inductor, di by dt is equal to V by L. Right? Now if you see here, this voltage is constant. Correct? This voltage is constant. So because the voltage is constant, this small v becomes capital V. And DC, small is for AC, variable, constant, capital. So V is also constant and L is also constant. That means your di by dt is constant.
Constant.
Okay, it's clear?
Yes.
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 Di by dt is constant means this is constant di by dt. And the slope is constant. You get a line. Okay. Then the inductor current will increase with the constant slope. And here also there is the DC voltage is constant. So it will also decrease with the constant slope. Okay? Get clear?
Yes, sir.
But if these two had been equal and the voltage sources are equal, there also 50 volt, here also 50 volt. So if the duty cycle had been 0.5, and this current would have reduced to 0. The duty cycle had been 0.5, the current would have reduced to 0. But because the duty cycle is 0.6, it is increasing more than decreasing. So there is going to be a current build up like this. Okay? It is increasing more, decreasing less, increasing more, decreasing less, increasing more, decreasing less. The question is, at the end of one cycle, And starting initially the current was 0. At the end of one cycle, what is the value of current? So we can find di by dt here. We can find di by dt here, that is equal to V by L. And V is how much?
Constant.
It's 50 volt. V is 50 volt, L is 10 millihenry. So you can find di by multiplying V by L by dt. You can find di by multiplying V by L by dt. How much is dt? 60 microsecond. Okay?
Yes.
That will give you the value of current here. Then again you find di, 40 microsecond. V by L multiplied by dt, 40 microsecond. So you get the value of current, you get the current rise, you get the current drop. The difference between the two, that is the value of current after one cycle. Whatever value you will get for 10 cycles, you multiply that by 10. That is the value of the current at the end of 10 cycles. Okay, if you calculate, you will get the value of current at the end of 10 cycles as 1 ampere. And then the energy stored in the inductor after 10 cycles will be simply half Li square. And because I is 1 ampere, it will be half into 10, 10 millihenry. Okay, so that will be, the answer to this question is 5 millijoules. Okay, was I clear? You have to work on this question slightly.
Yes.
This question you can solve because it was, you have done this in Nagpur University. A single phase full bridge fully controlled thyristor rectifier feeds a load comprising a 10 ohm resistance in series with a very large inductance. Very large inductance, your output current is constant. Rectifier is fed from an ideal 230 volt 50 hertz sinusoidal source through cables which have negligible internal resistance and a source inductance of 2.28 millihenry. If the firing angle alpha is 45 degrees, the commutation overlap angle in degree. You remember this question? Overlap angle is denoted by mu, correct?
Yes.
So you can find the value of mu. Okay, formulae are there. The formulae are there in PS Primera.
Yes.
This equation, this question can be solved very easily. Okay, stop here.
Thank you, sir.
Hello, sir. Hello.
Yes, Chetan.
Sir, thank you so much for your kind support and the lecture that was even today on power electronics topic. I hope your lecture is really helpful for the student to solve the gate question on power electronics. And I request to student, if any doubt, please ask the question to the sir.
They can ask me now, they can ask me later also. They can submit the questions to you, you can send them to me and I'll solve them and send them back.
Yes, sir. Okay, sir. Okay, thank you so much, sir.
Because right now they are not going to have any doubts.
Yes,
They'll
sir.
have doubts in this study.
So thank you so much, sir. We are associated with you for this kind of lectures and many valuable supports. Thank you so much, sir.
Thank you. It was my pleasure. And I think the quality of students was very good.
Yes, sir.
Okay. Okay.
Okay, sir. Thank you. Thank you so much, sir.